Alrighty, party people. Welcome to History Atom Notes Part 4. We're going to be talking about quantum mechanics today. So if you want to let people know that your brain is big, you can drop that term on them. Be like, what'd you learn today at school, Becky? Be like, it's not a big deal, Dad. I just learned about quantum mechanics. What's up? I deserve more cookies for dessert. Anyways, so here's where we are currently. The nucleus is tiny and small, but massive. It is at the center of the atom, and electrons kind of orbit around that guy. Whee! Yeah, here we go, having a good time. Like planets around the sun. If they are close to the nucleus, like this guy, it's probably got lower energy. And if they're farther away from the nucleus, like this guy, it's probably pretty high energy. And we also talked about how electrons, wherever they start, so this guy starts in this one, this guy starts in this one, but wherever they start, that's that electron's ground state. And if they were to jump up, because we added energy, that'd be their excited state, and so on and so forth. And each one of these rings represents a single orbit, if you will. Now, let's go ahead and take a look at the next pieces of history. By the mid-1920s-ish or so, we discovered that Bohr wasn't exactly correct. So remember, his model of the atom worked decently for hydrogen, the smallest element, the most simple element. I should say the most simple. But then it started to not work quite as well when you got to bigger elements like lithium, sodium, potassium, rubidium, so on and so forth. And so the model needed modified, but no one could do it. And the big question that people were kind of going back and forth on is an electron a particle or is it a wave? Some people kind of argue that it's a particle. Some people kind of argue that it's a wave. Electrons are somewhat mysterious in that sense. You're like, wait, how could it be both? So the answer to this question, is an electron a particle or a wave, is yes. It's both. It's both. An electron is both a wave and a particle. Which is crazy. But it is true, we so discovered. This conclusion led scientists to a new model. And at this point, we call this study quantum mechanics. Quantum mechanics. So let's talk about what kind of models we have now, what sort of players we have on the scene. So the first guy we got here, his name is Louis Victor de Broglie. De Broglie. Now, personally, I can't remember this guy. He's got his hair's kind of coming out there. I always thought he sort of looked like a piece. Oh no, I don't want red. I want. There we go. Yeah, I always thought he kind of looked like a piece of broccoli, to be honest. You know, especially if you kind of color that in there. But anywho, I can tell you guys are really laughing. I'm sure Emma's losing her mind right now. It's like, wait, how does he know? Anyways, de Broglie found that electrons have wave-like properties. Wave-like properties. And so he ended up with this kind of model of the atom where we have that small, massive, positive center of the nucleus. And then we have kind of these negative waves kind of around it. So we have these negative waves. These are no longer orbits, these nice predictable paths that we found that's not really true. They're kind of negative, I'll put neg for short, waves around that positive nucleus. And check out this little graphic here, this is pretty sweet. So as an electron, a wave, W, A, V, E, so we got wave there, or if I do a different color, you could say it's a particle. Pretty sweet, right? They wrote wave and particle at the same time. Oh my gosh. Let's go ahead and move on to our next person here. We've got Erwin Schrödinger. It's got this little double dot thing over the O. I can never remember what that's called. It's German now, I believe. And he developed a complex math equation to describe electron behavior. So let me see here. Where's his math? Let me see. He was super nerdy. So here are notes from his lecture. If I can pull this up. Where is that? There we go. Ivan Schrödinger. Notes from his lecture from Georgia Tech University. So I hope you guys are writing all this down. So we got the Schrödinger equation here, of course. Yeah, we just got to take some derivatives there. Got to divide both sides, of course. And then we got to consider the variables in the solution, of course, where there's your energy and your frequency. Don't forget about the Hamiltonian operator and then momentum operator. Again, I'm hoping you guys are writing every single word down here. And then we got our dependent portion, and oh my good gravy, it's so much. The bottom line is, this anyway results from the requirement that there be a node at the barrier edges, blah, 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 blah. We have wave-like properties, people, and his conclusion, if you want to sum it up, is that we have no idea where an electron really is. We have no idea where electrons really are at any given moment in time. No clue. No clue. So if I'm kind of scrolling down here, I'm back to Evan. Here we are. So that complex math equation found out we have no idea where an electron really is. We don't know. We don't know. And so those whole predictable paths where electrons are on those nice little orbits. Okay, so Bohr's like, all right, they're on nice little orbits and everything is perfect. We know exactly where electrons are at any given time and we can predict it. Yeah, that's not the case. So this GIF is really cool, or GIF, I don't know. But like, nah, nope, sorry, my TA Scott who had that tattoo, yeah, he's gonna have to go get some new ink because that's not quite how things work, all right? But yeah, it's kind of like this idea, if you take a look at, I have a couple of pictures here. Well, actually, no, we'll get to that with Heisenberg. But we just don't really know exactly where an electron is, which sounds like hard to wrap our minds around, but it is true. It is true. Let's talk about our last guy here. We got Werner Heisenberg. He's where the nickname for the guy and main character in Breaking Bad comes from. If you ever watch Breaking Bad, he calls himself Heisenberg. It's referring to this guy. He had the uncertainty principle. So here's what that uncertainty principle tells us. It is impossible to know the position and the momentum. So the position is the where, and the momentum is really the where is something going of an electron at the same time. At the same time. You will actually read about this. First time I ever came across this concept was in a history book where they mentioned, okay, so his uncertainty principle came out, and this is how it came off, is we're like, okay, at the most basic level of the universe, the atom and electrons, the smallest thing we know of at the time, we really just don't know what's going on. It seems random. We really don't understand it. There's so much uncertainty. And this really freaked people out. They're like, okay, well, there's uncertainty at the atomic level, and I'm made up of atoms. Is there anything certain about my life? Is my life truly just random? What about the planet? What about the solar system? What about the universe? And people kind of freaked out. There were some existential crises because of this. But it is true. We really don't know where an electron is or where it's going at the same time. And so we have to use probability where, like, okay, we're about 80% sure, 90% sure the electron is sort of in this area. Do we know that for sure? No. Can we tell you exactly where it is or where it's going? No, we can't. It's sort of similar. These are the pictures that I mentioned a moment ago. Take a look at this car here. So if you think of this picture of this car, you can tell me where this car is right now. You can kind of tell me where it is. Because you can get like some measurements. You can be like, okay, it is, this is a distance of 3 feet or something, and this distance right here from that cone to the bumper is 1 foot. And you can kind of tell me exactly where this car is going, or where this car is. But you can't tell me where this car is going right now, can you, from this picture? You could guess that's going forward, but you don't know that. What if it's parked? What if it's actually going in reverse slowly because there's traffic and they have to kind of go a different route? You don't know where this car is going. So you can see where it is, but you don't know where it's going. Or if you take a look at this car right here, we can see that this car is in fact going this way, but where exactly is that car? So I can kind of see a tail light like all the way back here, but at the same time it's also like all the way up there. So you're like, wait, where exactly is the back of this car and the front of this car at this moment in time? You can't really tell. And it's how electrons are, where you can kind of get a good idea of where it is, but you can't know where it's going. Or you can get an idea of where it's going, but you can't figure out where it is during that time. This is because the act of observing electrons, so we use light to observe electrons, it changes their behavior. It's sort of like, I as your teacher, I never exactly know who you are the way that your friends do, okay? So the moment, like if you are at the lunchroom, let's say, you guys will say certain types of things, certain phrases, whatever, that you would never say in front of your teachers. We know it's true. I'm not saying you're saying crazy things. I'm just saying there's things you tell your friends that you wouldn't tell me. That's a good thing. Okay, there should be a certain amount of distance between your teacher, as a student. So if I'm like, oh, I know exactly how these students are, they would never do or say that. Well, you guys change behavior the moment I walk in a room, and you might be pretty similar to how you are when I'm not there. But there's some changes that happen. It's not bad either. Just is what it is. And that's how electrons are, where the act of observing electrons being seen, it changes their behavior. And so that's why we can never know where they are or where they're going at the same time. Not possible. Not possible. So that brings us to our new idea. So no longer orbits, but we have orbitals. So we threw an ALS on the end there. Orbitals. Orbitals, they are regions of space where there is a high probability of finding an electron. So it's a general area where you'll probably find an electron. For example, if you're a betting person, where would you bet you'd find a bee? Well, you'd say you'd probably find them in a beehive. Now, beehives have, sometimes hundreds of rooms in them. Do you know exactly which room in the beehive? You're like, well, no, but, somewhere in the beehive. Or think about me. You guys only have me for one period a day, whatever time it is right now. But you don't have me the rest of the school day. Now, let's say you go, like, ninth period or something, you guys have Spanish. Okay, so after you have me for the day. Someone in this room probably does have Spanish ninth period. They're like, oh my gosh, is he talking about me? Maybe. Anyways, now, if someone's like, here, I'll give you $1 million if you can tell me where Mr. Pilcher is right now. And you're in Spanish, so you can't see me. Like, you have no clue. You're on the other side of the building. The correct bet you would place would be, I bet Mr. Pilcher is in room 245. That's this room right here. Are you right for sure? No. Do you know if I'm up at my desk, or if I'm up at the smart board, or if I'm up in the corner by the chemicals, or by the fume hood? You don't know that. You're like, okay, he's probably in this general region of space of room 245, but there's a 90% chance he's in there. He could be at the copiers, though, on the other side of the building. He could have gone to the bathroom. He could be in the lunchroom. I don't know. But he's probably in this general area. And you'd be correct 90% of the time if you guessed that I was in room 245 at any given moment during the school day. So an orbital is sort of like my room for me, where it's where I usually am, but not always. And it's not an exact point. It's like a general area. Now, orbitals, they can hold 0 electrons, 1 electron, or 2 electrons. Okay? It will never be more than 2, so that's the max. Okay? Orbitals can never hold more than 2 electrons in them. And they have all kinds of different shapes, sizes, and names. So orbitals have all kinds of different shapes, sizes, and names. And we're going to get into this, but there's this idea of like electron density. So here's all the places an electron could be. And it's more likely to be in there. And you could also kind of draw different orbitals around that. And we're going to see they have different shapes, okay? So, you got like a p orbital, d orbital, s orbital, all kinds of stuff. So we will get into that later next week. But so that's where we're going to stop with our History of the Atom notes part 4 for now. I have a couple of fun exercises, and I'm going to have you guys get into another worksheet that I mentioned to you in class yesterday. Now, if you kind of think about the particle versus wave thing, it's kind of fun if you look at these pictures. Don't say anything out loud for a second. Just think to yourself, what do you see in this picture? What do you see in this picture? Some might say, I see a young woman. And some of you guys are nodding your head right now, but yeah, I see a young woman. But other folks are like, what? I see an old lady. What are you guys talking about? So how is this possible? Well, some people kind of say like, okay, I see a young woman looking away. This right here, this is like the young woman's like, here's her ear right there. This is the young woman's nose. Here's like her eyelash, and she's kind of looking like this way. But other people are like, whoa, 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 I see an old lady. Here is the old lady's giant nose. Here is like her mouth, and here's like her chin down there. And this is the old lady's like eye, that kind of thing. So if you're like, wait, which one is it? Is it an old lady or a young lady? It's both at the same time. Depends on what perspective. And we got a couple more of these. So again, don't say out loud what you see. Think for a few seconds. Give people time here. Okay, so what do you see? Some of you guys see a rabbit, don't you? But other folks see a duck. So the rabbit, here's the eye. Here's this little nose, little rabbit nose. Maybe it didn't have whiskers coming off. I don't know. And then here's like the rabbit's ears. But if you saw a duck, the ears of the rabbit are really the duck's beak. And this is just the back of the duck's head where those whiskers were. They still have the sort of same eye looking to the left now. Interesting though, right? It's both a rabbit and a duck at the same time. Is this window opening in or out? Is it opening in or out? Crazy. If you look at just, this one's interesting. If you look at just like the bottom half, it kind of looks like it's opening in. But if you look at the top half, it kind of looks like it's opening out. Isn't that weird? So bizarre. So bizarre. But if you look at both at the same time, it's really trippy. You're like, what is happening? I've lost my mind. We do like one more. Let's go with this one. So some people would say they see a person's face kind of looking to the left, where, hey, this is like their nose, and this right here is their mouth. Here's like their chin. Whereas other times people say this is someone wearing like a winter coat walking into the night. So like this is the back of their head right here, and they're kind of looking this way. And they have like, maybe they're carrying like a lantern or something. And let's see here, what's the other one I got? Oh yeah, this one's good. What do you guys see here? A lot of people are like, oh, I see like a face or something. But what if, oh, it's the word liar, written in cursive if you turn sideways. Creepy, right? But anyways, electrons are both a particle and a wave. So like, does this say liar or is this some guy's face? Like, it's both. It's both. It's weird, but it's both. Now, that brings me to here. So you guys, and I already mentioned this yesterday, you're going to work on atomic structure worksheet number 3. So if you're my substitute teacher, if you wouldn't mind passing that out for me, that would be wonderful. Yeah, so this is the worksheet you guys are going to get cooking on. It should not be surprising at all. You need to make sure you can drill this into your brain as much as you can, because your test is next Friday. Next Friday. Next Friday. So again, I'll say it one more time. A week from today, you will have your test over Unit 4. Alrighty? Test on Friday. And then the 2 days after that are Thanksgiving break, or Thanksgiving week. We have Monday and Tuesday after that. We have a test next Friday, so a week from today, so you want to make sure we're gearing up, getting ready to go. The answer key to this worksheet is on the back of the paper that you just got with this worksheet on it. That's not a mistake. I did put the answer key on the back, so you guys can work on a few problems, then check a couple. So yeah, you are working on the rest of that worksheet during the rest of this period, or you are finishing up your guys' flame test lab from yesterday. So if you didn't finish your post-lab questions, take care of those, because I'm going to collect that on Monday when I return, okay? Email me if you guys have any questions, but have a great weekend, since I won't see you. So I will see you guys on Monday, and have a great time. I'll see you.